Hello, everybody. We're doing a new series now. I want to interview scientists who are not just doing the science that they do, but that also have other interests in educating the public or righting wrongs, as it were. People that have some interest in activism and in trying to make things better. Because I try to put a positive spin on as many things as I can. Today, I'm interviewing associate professor of geology at the University of Utah, I think it is. This is Dr. Benjamin Berger. He's a paleontologist, and he runs a YouTube channel where he tries to educate the public on various aspects of paleohistory. Dr. Berger, good morning. Thank
Good
you for being
morning.
on. And we were going to talk to you today about paleoclimatology, and specifically events in paleohistory that have resulted in where climate change has resulted in mass extinction events.
Yeah. So, I came in this morning. It's December, looking like Christmas. I am walking across snow fields. It's about, I don't know, 10 degrees Fahrenheit here in Vernal, where I'm broadcasting out of. A very cold day to talk about climate change. Um, and so I thought I'd talk a little bit about climate change, in part because it's a really hot topic right now. And there's a lot of people who misunderstand it on both sides of the aisle. There are extremists that are out there that think that climate change will completely destroy the entire planet and cause all sorts of destruction, and it can in the right context. But there's people on the other side that completely deny it or think that climate change might be a good thing for the planet. So I thought today would be a really good topic to talk about what happens during climate change events when the planet gets warmer. What happened during past periods? Many people bring up the idea that, oh, this is just it's happened before, and the fact that it's happening today, that the world is getting warmer, is not going to impact us very much because it's happened in the past. So a lot of times they say that without an understanding of what happened in the past when we had rapid global warming. And there are a number of things that are happening that we're seeing even today that we can see have occurred in the past when climate change has happened. So what I thought I'd do is give you a quick, brief history, the beginning about climate change and how we know the climate is changing, and a little bit about the history, because it's really quite fascinating. So if we go back like 100 years ago to like 1919, um, one of the issues at that time in 1919, if you can imagine, was that most of our climate records was based on weather records, just taking the temperature every day. So there were weather stations that were being set up around 1919, very simple weather stations to today's standards, where they could basically measure temperature, look out, see how cloudy it was. They could measure humidity. They had a barometer. They could get some degree of the typical weather that day, and they would have a weather report, and they would fill out that information. We had a lot of information, but we didn't have something really critical, and that is we didn't have a really good understanding of the chemistry of the atmosphere in 1919. And a lot of the innovations for understanding the chemistry, the composition of the air that we breathe, came about in the 1950s, right after the Americans dropped the atomic bomb after World War II. And there was a lot of innovation going on during World War II, in part because of fallout shelters. A lot of research was going into air quality in some of the bunkers in Europe, particularly in England, where massive, the entire city of London was having to go down into these bunkers and be hidden from the bombs. They had to make sure that they could breathe the air down in those places. So after World War II, there was, especially in the 50s, there was a lot of innovations for understanding the composition of the air that we breathe, the composition of the atmosphere, and how it changes. There was also a way in which you can understand the composition of the atmosphere to see if the Russians were testing atomic weapons. So there's a lot of money, especially with the military, the Navy, to do some studies to basically send a ship out into the Pacific Ocean, capture some of the air out there, and see if we could get some of these radioactive particulates that were coming from Russia, try to tease out if they were testing atomic weapons. So one of the people that came out of this was a graduate student. His name was Charles Keeling, and he basically in the 1950s was a student in California. And he had originally worked on uranium, and this is the 50s. That's where the money was. But he got interested in uh, doing atmospheric types of experiments. And one day, that is kind of the legend of it, is that he was going through some books in the library, trying to figure out a way to collect air samples. And he discovered that there was this inventor who had described a flask that was covered in canvas, a round flask. And what you do is basically suck out all the air in a vacuum of that round flask and then cork it so you make sure that there's no contaminants. It's a completely vacuumed ball. And then you could take that ball, that flask that's covered in canvas so that the glass doesn't shatter underneath that vacuum, and take it out, and then you could just uncork it. And the air would be a vacuum, would get sucked in, and then you pop the cork in, and you could take it back to the lab. And you would have in this little ball, this flask, you'd have a sample of the air at that moment, at that place. So one of the things that he would measure when he would capture this air sample was CO2, the amount of CO2. Now, CO2 varies quite a bit. We breathe it out. So if you are underneath your bed sheet at night and have the pillows pulled over your head and you're in your blanket, you're breathing out a lot of CO2. And so the CO2 level will rise, and you can actually feel it, when you're underneath the bed, you can feel like you're suffocating. A lot of that is because of the buildup of CO2. And if it builds up too much, it can be lethal. So one of the things he did with CO2 that's really interesting too is that it's a fairly large molecule, meaning it sinks. So the first thing he discovered by doing these experiments was that there's a daily cycle to CO2. So during the day, when the atmosphere warms up, the sun's hitting the earth, the CO2 will rise up. And then at night, as it gets colder, the CO2 will sink down. So CO2 rises at night and then it falls during the day, just on the surface where we live. So this is interesting. And so he thought, I wonder if there's a yearly cycle to CO2. Now, this, of course, required taking measurements for an entire year. The problem that he had in taking those measurements is a car would drive by, or you breathe on it, or, there would be all sorts of things that could contaminate it with extra CO2. A factory all of a sudden, or forest fire nearby, some sort of a bunch of CO2 would enter it, and that would ruin his experiment because he wouldn't be able to figure out what the natural cycle was for a yearly cycle. So they basically tried to petition the government to do a couple experiments, and his ideal choice was to get some air samples in Antarctica. Because Antarctica would be perfect. There's no factories, there's no cars, there's not a lot of people, and there's no forest to burn down, so there's not going to be this contaminant CO2. So it was difficult to fund this because you imagine having to go to Antarctica and open up this flask every single day, record your observations for an entire year in freezing Antarctica, and for science. He was able to get some people on ships that went around Antarctica in 1958 to basically uncork these things and get some samples, but not enough for an entire year. He had another choice, another place that he selected, and that was Hawaii. Now, Hawaii was, again, not ideal because there are cities around Hawaii, there are people, there's a volcano, but it's in the middle of the Pacific Ocean. And if you station it on top of the tallest volcano in Hawaii, the wind patterns and stuff, hopefully there's no big, huge coal factories and things like that might contribute to it. So that was the second choice. And he could get people to live in Hawaii year round, much more than people living in Antarctica. So he set up a station in Antarctica, or I'm sorry, not Antarctica, in Hawaii, and they started measuring CO2 to see if they could get a yearly cycle. And they did. There's a yearly pattern. It rises in the winter, usually in January, February is when it gets to the highest amount, and then it starts to drop down. It drops down this spring. And this yearly cycle is really interesting because it is related to the changes that are happening in the forests in the northern hemisphere. So there's more forests, there's more boreal forests in the northern hemisphere, and those forests lose their leaves. They in the autumn, in the fall, they lose their leaves, and they basically are not producing a lot of biomass. Then in the spring, all those leaves come out, new leaves, and they draw down that CO2 because plants need that CO2 to survive. And so it's this back and forth. This is the thing that Al Gore calls the breathing of the earth, this back and forth of CO2. Really exciting. But they had some funding to continue measuring CO2. And as they started measuring CO2 year after year, starting in about the 1960s, they started noticing that there was another trend, and that was an upward trend of CO2. And by the 1980s, they sort of realized that CO2 was rising. And by 1992 was when Al Gore started doing the congressional reports on climate change, came out in 1992. They had really seen the trajectory of CO2 rising quite rapidly. About that time, there were two paleontologists, a guy named Norman Newell and Leslie Marcus, who were in New York, and they wrote a really obscure paper. Not very many people know about it. But they basically said, this trajectory of rising CO2 is probably related to population growth. That the reason that we're seeing CO2 is that more and more people are buying cars. There's more people on the planet. There are more people who are using electricity and generating, more and more power. And that's producing a lot of fossil fuels, and that's leading up there. Now, one of the things, sort of the smoking gun that we need in determining where that CO2 is coming from, has to be in a marker, something that we can actually say, okay, this rising CO2 that we're seeing in the long-term trend, where is that CO2 coming from? And the marker that we can use is in the isotopes of the carbon. So carbon is not just carbon. There's actually two types of carbon. There's carbon-12 and carbon-13. There's other carbon, like carbon-14 that you may have heard about. Carbon-14 is radiogenic. It falls apart, and it falls apart very rapidly. About half of it falls apart within 5,700 years. But carbon-12 and carbon-13 don't ever fall apart. They're stable, so they stick around forever. So there's two different flavors of carbon. Now, the interesting thing about these flavors of carbon is that one flavor of carbon likes to bond with oxygen more than hydrogen. The other one likes to bond with hydrogen more than oxygen. They both will bond with either one, but they do have different flavors in terms of who they most readily bond to. So carbon-12, which is the lighter carbon, loves to bond with hydrogen. So if you ever use natural gas, you light up a stove with natural gas stove, the natural gas that's burning is carbon bonded to 4 hydrogen. So it's going to tend to be more lighter. In fact, actually, it's really light compared to other places where you find carbon. Carbon that you find in limestone is bonded to an oxygen. It's going to have a lot more carbon-13. It's heavy, tends to have the heavier carbon. So one of the things we can do is we can look at the composition of the carbon in the dioxide in the atmosphere. Is it more 12 or more 13? And we can look at that ratio over time. And so scientists have done that, and you see that there's a lot more carbon-12 being added to the atmosphere. That indicates that it's the burning of methane, of natural gas. It's the burning of octane in gasoline. It's the burning of coal. Those are resources or reservoirs of carbon that are abundant in that lighter carbon-12. So that's why we know that it's coming from fossil fuels and it's not coming from someplace else. So what's really interesting is what happened after Al Gore lost the election in 2000. So there was a big group of people that were really advocating for, all right, we got to deal with this buildup of carbon-12. It's getting pretty high. As it builds up, it's a greenhouse gas. It's going to cause the earth to warm, and we're starting to see temperatures warming up. Now, by the 90s, we had satellite data that was coming in, showing us the retreat of glaciers. We saw data coming in. If you go back to people like James Burke, the science documentarian from England, he has a whole series about the rising CO2 and the danger of it that he was producing in the 90s when I was a kid. So one of the interesting things is that when Bush won the election, this was a hot topic, and he had to kind of deal with it. But his family came from oil money, and there's a whole bunch of people in the oil and gas industry who were kind of freaking out about this. If people quit using gasoline, combustion engines, switch to electric or new technologies, that would devastate that economy. And so one of the things that he did, which is kind of a funny story, is that he was like, we need scientists. We need good conventional scientists. And so he was looking through a bunch of papers, scientific papers, and he came across this wonderful paper. It's a very classic paper, well regarded, by a scientist named James Hansen. Now, James Hansen at the time was he was the director of NASA's Goddard Institute in New York, and basically it's an institute at NASA that looks at the Earth and looks at the climate of the Earth and changes in the climate. He had written this wonderful paper about global cooling that happens. And I think that caught the politicians' eyes, the Bush administration. They're like, oh, scientists that's advocating global cooling. Excellent. We'll bring them in. We'll bring them in. Now, this paper is a really great paper because what it does is it looks at the Earth and took in all of the satellite information, all these temperatures that were coming in. And they looked at volcanic eruptions. And one of the things that they noticed in this paper was that when there was a big, huge volcanic eruption, that global temperatures would drop about a degree, not much, just a little drop. But the data they had, these huge pools of data from all around the world, would show that there was this wonderful little drop in temperatures, 1 degree. And it only occurs, like about the year after a big volcanic eruption. And it was a really wonderful paper to show that what was going on was that when you have a big volcanic eruption, that ash gets sent out into the atmosphere and it basically blocks the sunlight. So there's less solar radiation getting to the surface of the Earth, and it cools things down, just temporarily, just a little cool down. Well, the Bush administration saw this and they were like, oh, let's invite him in. It's a global cooling paper, and he'll be an advocate for the opposite opinion. And so he came in, and he documents this in his book, which it's The Storms of My Grandchildren, I think is the name of it, but you should look it up, James Hansen. So he comes in to meet with Bush, and they sit down and they said, what do you think about this rising CO2 and global climate change? Is it all bogus? No, it's not. It's like, my paper is about volcanoes. It's not about CO2. And yeah, climate change is a big, big issue. And in the same room with him was a guy that had been a lobbyist who had worked for many, many years in the tobacco industry, lobbying on behalf of the tobacco industry. And he was invited in. He was one of the early climate deniers. And he was in this room with this guy, and he's like, they're yabbering back and forth, and he was like kind of freaking out. He's like, no, this is a really big issue. We need to address it. And one of the things he suddenly realized was that politicians were not listening to scientists. They were listening to these lobbyists. And there's a funny anecdote where he's debating about climate change, and they kept referring to this lobbyist who was not a scientist. He had advocated for the tobacco industry. And he talks about this in the book, and it's really profound. When they walk out of that, they get in the car, and he turns to the lobbyist and he said, so you do know that cigarette smoke causes cancer, right? And the tobacco lobbyist said, no, tobacco, you can still smoke. It's totally fine. And he's like, oh man, I should have brought that up. This guy's a lunatic. Nothing will change his opinion, no matter what you do. And that's the mentality I think that many politicians have, is that they have a voice from lobbyists who do not change their minds. They are there to represent the tobacco industry. They're there to represent the oil and gas industry. They have a purpose to change other people's minds, but their minds will never be changed. Scientists, on the other hand, are kind of in the realm of, we look at the data. We're happy to change our ideas. So this sets up my history. So I got a degree in geology. I have many friends who work in the fossil fuel industry. I have worked in the fossil fuel industry, and I'm teaching a class next semester on how to find oil on the ground. So I'm a geologist. It's what geologists do. There's a huge segment of geologists that work in the petroleum industry. It's a huge part of the economy in the United States. But I wanted to understand a little bit about what happens in past periods when climate changes. Yeah, the climate's changing, but does that mean that we're going to all go extinct and die out? Or what's going to happen to the planet when climate changes? How can we, if politicians don't change their ways, if there's no laws passed, if we just continue the same old story, what happens when CO2 is double what it is now in the atmosphere? What if it's triple or quadruple? What changes would we see on the Earth? So, like, if you were, 100 years from now, wake up and we haven't done anything about climate change, what would the world look like? Those are the questions that we wanted to ask. So, I began working on an interesting project looking at a period of time in Earth's history when there was abrupt global warming. It was an event called the Paleocene-Eocene thermal maximum. And I went back to school to get my degree, my PhD, to study this event. And it
You
occurred
said Paleocene, Eocene?
Paleocene-Eocene, yeah, thermal maximum. And so back in,
How does that differ from the KT boundary?
yeah, so I'll explain a little bit about
Yeah.
how it was discovered. And actually, the KT boundary plays into this. So back in 1980, when Walter Alvarez published this really famous paper about this asteroid that impacts the Earth and kills off the dinosaurs. Scientists were like, "Oh, that we got to study this, and we want to confirm this by having as many places around the world go through that KT boundary and document that change and see if we see the same chemical signatures in the rock that caught, whether there was asteroid debris in that zone." They had money back then, and they bought a oil, basically from an oil company. It's basically a ship with a drill rig on top of it, and they could take this ship out and drill into the Earth at various places in the ocean. And they bought this for kind of a pittance from an oil company, and then they staffed it with scientists. And their mission was basically travel around the world, drilling cores into the Earth and studying it, and try to get down to the KT boundary to confirm that this was possible. So as they started doing this in the late 80s and early 90s, they would just go around. They're still doing it, still really active research, and on the ship and drill down and basically bring up this core. And they were drilling down to the KT boundary. So as they were drilling down to that boundary to look for it, they would basically look at the fossils in the core of the rock to determine the age. And they noticed there was this really weird red band and this really change in the carbon isotope ratio in that red band. And this red band was above the KT boundary. It was in the late Paleocene strata. So about,
hold on for a second. For people who aren't conversant on their different geological ages, how many years ago was that?
So this is 55.5 million years. So it's about 10 million years after the extinction of the dinosaurs. So it's above it. So, in these cores, it would be
So not related to it.
not related, be above it. And it would be above it by several meters, like 20 meters above the KT boundary. In some sections, it might be 50 meters or 100 meters. So, but it was always above it. And it was this red band that they would see in it. So they started looking at the oxygen. And so you can look at oxygen isotopes in marine sections and use that as like a paleothermometer. So the ratios there are related to temperature of the ocean waters. And they found that that in that red band, there's this huge increase in temperature, a very abrupt global warming event. And they were like, whoa, this is really weird. And they then correlated into terrestrial rocks, like in Wyoming, where they made the same samples. They looked at the carbon and looked at the oxygen, and they realized that it corresponded to what geologists have established between these two epochs, the Paleocene, which is the epoch right after the Cretaceous, the end of the dinosaurs, and the beginning of the Eocene. And so it became known as the Paleocene-Eocene thermal maximum. And so people are like, oh, wow, this is like a wonderful event in Earth's past where temperatures rapidly warmed. The estimates are between 6 to 10 degrees Celsius increase in ocean temperatures. So that is a pretty severe global warming event. They're talking with the, politicians are talking, trying to bring it down under 2 degrees Celsius global temperatures. This is 6 to 10.
And just to give people an idea, because I know, as my wife pointed out, there are people that are not conversant. When they talk about climate change varying by a degree or so, that the problem that a lot of people have is that, well, it was 10 degrees warmer yesterday, or warmer today than it was yesterday, something like that. And you can do that in one location at one time. But when you're taking all the temperatures for everywhere in the world and averaging them together, then it's very difficult to get a difference of a whole degree.
Yeah, and a whole degree doesn't sound like much. I mentioned a whole degree with the volcano eruptions. It's colder, but it'd be a colder winter, but it's not going to be something that's going to be really affecting too much of the weather. I mean, it'll affect some things. Things will be warmer. There'll be less snow. There may be less water from the snow runoff in the
People don't
river.
realize that there is a significant difference if you have a global annual average of 1 degree difference. The other factor is that it's not just everywhere in the world; it's everywhere in the world over an entire year. So again, it makes it even harder to change by a degree. So if you have a change of 1 degree, there is a significant there's differences you would notice, and if you have just as like 4 or 5 degrees, then it's really significant. Okay, so
What do they think caused this thermal maximum? Was the sun at a maximum period, or how long did it last? Also,
okay, so so everybody is like, what is this thing? How long did it last? The other question we have is like, what caused it? So how long it lasts? It's the recent estimates still debated because we're talking thousands of years, so it's a very abrupt event. The lowest I've seen is 11,000. Scientists advocating 11,000. The longest I've seen is about 100,000. Most estimates are around 70,000 for the PETM. There's actually some good, so we're talking just a few thousand years. Now, when 10,000 and 70,000 sounds like a huge amount of years. However, the initial increase in temperatures was probably on the order of just a few thousand, maybe fairly short, maybe 1,000 years. So it's kind of equivalent. In fact, actually, it's one of the most cited equivalent events to study to compare with modern climate change, because it's a very abrupt event. It's not like a gradual ticking up of temperatures, which you saw like in the Cretaceous. It's something that's really abrupt very quickly. And that's one of the really neat things about this event, is that it's a very quick event. Now, what caused it? Now, there's a lot of debate out there, a lot of information. One of the studies that I think is really important is a study that was done at Rice University by a geologist down there. And he looked at barium, and he noticed that there's an increase in barium. There's a study that just came out looking at some other chemicals too, and it seems to support this story. So barium is a weird element. It forms barite, but it tends to be very abundant in the deep ocean, in the very deep ocean where it builds up. It reacts to the sulfur in the soils, in the ocean sediments very deep down. And it tends to get locked up in some of these deposits of methane. So methane is produced by the breakup of organic material deep in the ocean. So when dead things fall down in the ocean, they go, "Wah," and they fall down there and they're dead. And once they're down there and they're dead, they start to break apart. And if you break those carbon bonds, if you keep breaking them down, you eventually get to methane. Now it's so deep, there's a lot of pressure, and it's cold. It's near freezing down there, and there's a lot of pressure of that water. And the methane becomes a solid, becomes what's called a methane cathode. And that methane locks up a lot of that barium. Now, if that methane were to come out of that solution, become a gas, it would come up and bring up a lot of that barium with it. So one of the things that they've noticed at the PETM is spikes of barium. And so the idea, the theory is that there's a lot of methane deep in the ocean, and it switched from a solid to a gas as temperatures warmed up. And when that happened, it released a lot of this methane into the atmosphere, which then oxidized and formed CO2. Now, to support that is that red band. That red band scientists puzzled over. They thought maybe it meant that there was more runoff, changes in the deposition. But what they discovered was that that red band actually represents an ocean that turned acidic. So when you increase CO2 into high, like twice, maybe 3 times, maybe 5 times, maybe 10 times more than it is today, the ocean becomes acidic. It takes in a lot of that CO2 and forms carbonic acid. So it's basically the same thing that you get in soda pop. So carbonated water is basically CO2 added to water, and it becomes very acidic. And when the ocean becomes acidic, it means that any organism that produces skeletons formed out of calcite, like corals, little forams, plankton, they all basically die. And what you have then is that red band is the absence of the carbonate life forms, their skeletons, because they're gone. And this is a big worry of climate change. It's not the temperature, it's turning the oceans and making them acidic. Because this will kill off a lot of ocean life. Because a lot of ocean life relies on having a water chemistry, a pH that's going to be more neutral. In fact, a little bit, have a lot of those calcium ions that they can pull apart. When you introduce a lot of this stuff, it makes it acidic, and it really is harmful for a lot of these things. This is why
aren't a lot of ocean organisms adapted to a very small range in acidity too and pH?
Yes.
Kind of like in an aquarium, if you get your pH wrong, the whole aquarium.
Yeah. I mean, fish don't survive in soda pop water, in soda.
This was something that when I was working on my systematic classification of life series, and I come to the period of the great dying, that was a disturbing thing to do all of the research for that, and to see why was 95% of ocean life wiped out in that period. And it was, and as if for people, as my wife pointed out, who are not conversant in this, a similar thing. The global temperatures rose because of a massive volcanic eruption the size of the United States, and the result of that was that the temperatures got up to the point that it released the methane that what is it? How many? I forget how many trillion tons of methane are in the ocean floor. But once that started erupting, well, then it rose the global temperature another 5 degrees.
Yes.
And
yes,
killed just about everything.
So one of the things we have is that when methane, if the temperatures keep warming, the temperature of the oceans then becomes important. Because when it becomes warm enough at those really deep depths, then you release the methane. And it's like releasing the Kraken, this, methane gets up into the atmosphere, it's going to oxidize, and it's what we call positive feedback. It's going to push the climate even warmer.
And while methane doesn't stay in the atmosphere very long, it's 80% more insulating than CO2. So it's a much, much worse, orders of magnitude worse greenhouse gas than CO2 is.
So that's kind of analogous to now that these rising temperatures will also release methane from our oceans, and it will accelerate the temperature change.
Yeah, so we're looking at ocean acidification. We're looking at the release of methane happening in the future. Right now, there's something called a CCD, which is the carbonate composition depth. It's a depth in which shelly organisms can compose their skeletons out of calcite. It's a very important measure in oceanography. And there's a paper that came out in Nature not long ago where it's rising at a really remarkable rate. And if that hits the surface, comes up into your ocean, there will be things that survive. Fish do well. They do okay. But the things that they feed on don't do very good. So it's going to affect coral reefs dramatically. We're seeing a lot of coral reefs dying off, and that's part of that ocean acidification. You bring up we'll talk about the Permian-Triassic boundary, but when these events happen, the coral reefs just really die back. They really suffer during these events. They do much more when you have more basic ocean temperatures, ocean chemistry. So that's a big danger with the, but then, okay, so you're like, all right, well, the oceans are kind of screwed. It's warmer, but, what about farming? What about on land? What was going on land during this period of time? Yeah, the ocean's, not doing very good, but what about land? So, when I was a student, I basically looked for the boundary, the Paleocene-Eocene boundary in Western Colorado, where I did my dissertation research. And that was the question I was asking, okay, what happens to the animals living on the land? Do we see an extinction? Do we see that they are not affected by it? Do they just survive and do well? Do we see increased diversity, decrease in diversity? What happens to the animals living at the time? And we can also, there's a researcher at the Smithsonian named Scott Wing. He's asking the same questions about plants. What were the plants doing during this period of time? Do we see a diversity of plants? And one of the interesting things is before the discovery of this global warming event, many paleontologists had said, well, this boundary is really interesting because it's this diversification of life. You see a lot of diversity. There's not much change in the plant faunas. It just, looks like we got through it. Okay. Now, one of the problems, though, is that it's a short span of time. And so you got to find strata that spans that time, which is really hard to do in a terrestrial environment. And Scott Wing, who studies plants, worked in the Bighorn Basin in Wyoming, which has some deposits, rock layers that span this boundary. And he started looking for plants, and he'd find them above and below. And the forests that were living at the time looked very similar. So he's like, not much change. But then one year he found a plant locality, some fossil leaves that were in the boundary. And within that zone, when the climate was changing, the forests looked completely different. And they're dominated by the hackleberry tree. Now, the hackleberry tree, we have some in the campus here, is a really great tree for roadsides, near roadsides, because it's drought tolerant. It doesn't get very big. It produces these really hard seeds too that paleoclimate people use. But it's this wonderful tree because it doesn't require much in the way of water. See, a drought tolerant trees all of a sudden in this zone. Above and below, when the temperatures were brought back to normal, you saw a normal forest, very diverse, semi-tropical forest. But that sparked his idea that something was happening to the forests. And I started looking at the mammals, and some of the mammals, you see this huge change in the number of mammals that you have. So in the Paleocene, you had this whole group of arboreal mammals living in a healthy forest. And they were bizarre mammals that we don't have today, things like multituberculates, plesiadapids, very common. But then when this event happened, above it, you get a very different fauna. You get true primates and you get rodents, became really, really common. So what was happening was that the forests were disappearing. And there's some evidence from England and Europe as well that one of the things that was happening that is causing this deforestation at this event was forest fires. So you have on land forest fires. And this is something we're observing today. Forest fires in California destroyed 24,000 people's homes. So huge, forest fires is a huge problem. And you see that in the Paleocene-Eocene thermal maximum. It changes the nature of the animals that are living. It takes out the forests. Many of these species survive a little bit into the Eocene. They're not completely wiped out by this change, but they become less dominant. And you see the immigration and the invasion of other species from other places that come across. This is part because you have an ice-free Arctic, so it's easy to get across from Asia, and you see this cosmopolitan group of species. So you look at the species at the Eocene after the event in Wyoming, they're the same as you would find in France.
So, like in California, the plants adapt to drier conditions, requiring less water, and they're also drier themselves, so they're more prone to forest fires.
Well,
So
they don't
that's
have
what.
time to adapt, so they just burn. You know, imagine like you go to California, Southern California, and drive around Arizona, these places. The trees that were living there can't adapt to the climate now. So climate has changed, so it's drier. There's not as much water, and so because they're water stressed, and they just add fuel to fires. So these fires can become really dramatic. There's nothing to stop them. All the forests die, and the fires just burn because there's not water. You know, there's very water scarcity becomes an issue in climate change. So forest fires become the next sort of ticking point. And you see that at the Paleocene-Eocene thermal maximum.
Yeah,
Now,
it's analogous.
Yeah.
When we were in Fresno, there was some people that were talking about how in a good climate, the redwood trees, for example, can withstand and survive a number of forest fires. That the temperature doesn't get to be enough to actually light the tree on fire. And so that you can see indications in some of the dead trees that they had survived a number of forest fires and just lived right on through it and kept going. Which people don't realize that a tree has to be dried out to some degree before it'll light up.
Yeah. And these fires are in the Paleocene-Eocene, you're talking redwoods across the entire United States. So you're talking about destroying all of those redwoods across not just in one place in California where they live today. So,
and that's another thing to point out is if we had redwoods all over the United States, and now we have them only in one place in California, that this is how some things come back when the climate change, like we go through that period where you have this one type of drought resistant tree, and then you have the regular forest replaces that later on. People will be wondering, well, where were those trees at this other time, and where are the corals during the rest of this? I mean, that there are little packets, or there are little pockets of places where, for whatever geological reason or geographic reason, they're relatively protected against the rest of the global environment. Relatively,
yeah, it's a little refuge.
some things that'll survive in that little hole where things are all right for that time, and then when it becomes conducive everywhere else, and then because the temperatures or the chemistry of the ocean is not going to be exactly the same in every place for various reasons.
Yeah.
Also, when you look at the event you're talking about, people can get maybe too optimistic and say, well, the Earth survived and a lot of things survived. And the Earth will survive this climate changes if it continues. And life will survive, but that doesn't mean humanity will survive. Doesn't mean a lot of other species are going to survive either.
You might have a handful of resourceful people that manage to entomb themselves in some little man-made environment until they manage to survive this.
Fires, forest fires. All right, we're gonna play the devil's advocate here. Forest fires, we can survive. I'm gonna live in the city. I'll live in an apartment complex. I don't have to worry about forest. Well, we talked about positive feedback before with methane. Well, forest fires is releasing a lot of CO2 into the atmosphere as well. So all of a sudden you have another positive feedback. So forest fires, that CO2 is going to increase. But you're like, I'm living in an apartment. Sure, the temperature's warmer. There's less days of snow. That's all good things, right? I don't live in, maybe you don't live in Phoenix. So, I have air conditioning. We'll survive. We're humans. We can survive this. Maybe, you can't buy fish at the market anymore. You can't, you love seafood, but you just can't find it anymore. It's too expensive, or, it's all farm raised. So, but we'll survive, forest fires. Yeah. Just don't build that cabin up in the woods, or if there's a forest fire that comes through, you're going to have to rebuild it, and it may not look pretty as you imagined before. But humans will survive. So it's kind of an annoyance, but not the end of the world. In fact, one of the interesting things, if you look at animals that survived the Paleocene-Eocene thermal maximum, mammals, the thing they have in common is they're all terrestrial, very mobile creatures, dog-sized, like little condylarths and things like that survived. They're little hooved mammals. They could move, they did fine. When the forest fire came, they would just move out of the way. They could move back and forth. If it got too hot to the south, they would move to the north. And humans were pretty mobile. We can move around really fast. So, all right, so you're thinking, all right, so that's not too bad. Now we can step it up. And you mentioned this event before, and that's the Permian-Triassic boundary. And that's like the next step above the PETM. So you can say, well, we can survive a PETM event. Yeah, global temperatures increase 6 to 8 degrees. This means places like, New Jersey would look a little bit more like Saudi Arabia. You would have a lot of, dune features when you drive around cross country. The dune fields in the Midwest and in eastern Colorado, the Great Dust Bowl, those would be daily occurrences. There would be quite a bit of areas that would be no longer able to irrigate. You would have food scarcity would be a big issue. So prices of food would rise quite dramatically. Immigration would be a big issue. People in Mexico, people in the South would be wanting to move north into North America, or into the United States. People in the United States would be wanting to move to Canada as people are trying to kind of avoid these areas just getting too hot.
And we want to move to Canada already, but for different reasons.
Yeah, I mean, you're going to see this migration. You're going to see Canadian politicians being like, "This is a good thing," while politicians in Mexico are going to be like, "This is a bad thing. This is affecting us more than you guys up there. Things, you don't have to deal with as much snow, and you think it's all positive, but we down here are having to deal with all this, really, really hot days, lethally hot days." So it's going to change, geopolitically, a lot of things. Wars will start to spark. The military is very worried about this because it'll cause geopolitical instability. But we'll survive, we'll survive. So the Permian-Triassic boundary is when things get really bad. Now, the Permian-Triassic boundary is caused by a different thing. It's caused by a volcano called the Siberian Traps in Siberia. Massive, huge volcanic eruption occurred 252 million years ago. Very old. This is before the dinosaurs. This is the advent. This is the climate change that spawned the dinosaurs. It occurred very long ago in history. And what was happening at this time was that forests had taken over the earth during the Carboniferous period. Huge amounts of forests. In fact, the coal that we burn today, much of it comes from the Carboniferous period. The entire Appalachian coal field, the big West Virginia, Pennsylvania, those big coal-producing parts of the United States, as well as most of the coal in Europe, all comes from the Carboniferous. So huge massive amounts of biomass was buried into the earth. And when this volcano erupted, it ignited this coal, and it basically sent this coal up into the air, the CO2. Now, what's interesting about the Permian-Triassic boundary is that when a volcano is erupting, there's no stoppage. There's no turning the off switch. It just keeps going, no matter what's happening to life forms on the planet. So this is the most extreme case because the amount of CO2 that was injected into the atmosphere it's difficult to get estimates on it. It's difficult to figure out what the amount of CO2 in the atmosphere was at particular times. I'll mention a little bit about that later on, but
what people need to understand if they're not conversant in this is when you
say, all right, so we can't do
it. You say it's a volcanic eruption, but people don't understand that this was a flood basalt eruption.
Yeah,
it's very different than there's never been a flood basalt eruption at all in human history. They've happened many times in geologic history, and every time they have happened, they've resulted in extinction events. Yeah,
not all of them do. So there's some big ones. The big ones do cause some issues climatically. There's a famous basalt flow that happened during the Miocene in western Colorado, where I'm from. So if you drive across the United States and pass through Colorado, you actually run into these. So down near Battlement Mesa, the top of it's capped by a basalt flow. There's these big volcanoes. They erupt. They send basically lava that changes when it cools down, becomes basalt, and they can flow over really long areas. And you see this in Hawaii with the basalt flows coming down and where it's kind of gobbling up towns and stuff. So imagine a basalt flow like that that's gobbling up an entire, basically, as you said, an area about the size of the United States, continental United States, a huge area of just this basalt flow flowing across. When basalt hits rocks, it starts to melt them, releases a lot of gases. But if it hits coal, it's releasing a lot of that CO2 as well. Now, it releases CO2, but most of that CO2 is going to be that heavy CO2. Doesn't mean it's better CO2 anyway, but it's going to have a different chemistry. Most of the chemistry that we see from the Permian-Triassic indicates that it's coming from light carbon, similar to coal. So it's really that huge impulse of CO2, which is more analogous to what we're doing now with burning of coal. So coal was being burned at an incredible rate about 252 million years ago. We see the oceans becoming acidic, like we did at the PETM. We see global temperatures in the Earth's oceans becoming extremely hot. A lot of this is driven by some amazing geological research being done at Chinese universities, particularly because in China they have a wonderful deposits and layers of the rocks that represent this period of time. We have it here in Utah. It's also been studied in South Africa and Australia, Antarctica, but a really good record in China. So the Chinese scientists have been studying trying to figure out the temperature during this event, and it's unbelievably hot. So we're talking, hot tub-like temperatures of the world's oceans. So jacuzzi, the oceans turn into a jacuzzi, which is not good for animals. But there's some other things that start to happen. We see the absence of forests disappear. We see desertification. The rocks change. They start to be sand dune deposits on a massive scale, much more than we saw at the Paleocene-Eocene thermal maximum. So the forests don't come back after this. Things get really bad during the Permian-Triassic boundary. One thing that can happen is that the CO2 gets so high in the atmosphere becomes unbreathable. So OSHA regulations regulate about 10,000 parts per million. When CO2 gets about 1%, it becomes lethal. In fact, you basically get kind of confused, you fall over and you die. Many people are very aware of this because of the mission Apollo 13. If you've seen the movie Apollo 13, if you remember, during that mission to the moon, they had the explosion, and the astronauts had to get into a separate space capsule that was designed for fewer people than they were in there. I think it was designed for one person, but 4 people had to get into it, which meant that they were expiring CO2. And in submarines and in spacecrafts, they have a CO2 scrubber. It scrubs out the CO2 with a chemical reaction, gets rid of that CO2. Because if it gets up 1%, 2%, it's going to be lethal and the astronauts would die. So they basically had to kind of invent a better scrubber to accommodate the more astronauts, because they were sitting down doing their calculations and they realized by the time they got back to Earth, they would have produced so much CO2 they would have died. And so that's what the big drama of that movie, that's the big drama of that mission was, can they get back? Can they get the CO2 back down to low levels? CO2 is very dangerous for people who deal with dry ice. Because dry ice is basically frozen CO2. It's solid, and it sublimes into a gas. So if you breathe in a lot of that CO2, it causes a lot of asphyxiation. It actually, that CO2 gets in your bloodstream and it causes you to die. So CO2 could get to lethal levels. Now that's a huge amount of CO2, but during the Permian-Triassic boundary, CO2 probably is getting up into very lethal categories. Many of the animals that live and survive through that were burrowing animals that were specialized for being able to breathe high CO2 gas. Mammals that live today that can do this really well are marsupials, because marsupials have to live in a pouch. They, as they're developing, they're breathing in a very high CO2 air, more than ambient air outside of them. So they're pre-adapted for an atmosphere of high CO2. We're not.
Would that explain why the marsupials are the only surviving metatherians?
It could. And the other thing about marsupials is that they were able to have live birth, which there's a definite advantage of having live birth versus
Eggs.
so the monotremes are still, okay. They're not, but they're not as diverse as
No, I don't mean monotremes. I mean metatherians. I mean,
metatherians.
yeah, people are not aware that that marsupials are the sole surviving group of a much larger category that was separate from eutherian mammals like we are. There was a much larger category called metatherians, and despite all the diversity that there once was for metatherians, marsupials are the only ones we have left. And so I have to wonder what's different about them that every other category it all died out.
Yeah, it's kind of interesting. So there were a bunch of other things, yeah, as you mentioned, that were living during this time. Part of it was, I don't know exactly what's driving. What's interesting about marsupials is in the Cenozoic, when they're global. We find them in Africa, we find them in Europe, I find in North America. But in Australia today, they do quite well. And that was part because the competition was slightly different. They weren't having to compete with other animals. That's the theory. It's interesting too, because, you do get marsupials up until in the Eocene of Africa, and then they disappear in Europe. And we have a marsupial that's native here in North America, the Virginia possum, which is actually pretty successful. And it's interesting why we just have that one, where South America has more, and Australia has pretty much the gold mine of marsupials. So it's kind of interesting. But yeah, so going back to the way back time machine, way back to this event, things were getting bad with CO2. So that's one thing we have to worry about. So even if you're living in an apartment in a city, you have enough money that you can deal with the high prices at the grocery store. The next thing that's going to affect you is actually the amount of CO2 in the atmosphere, being able to breathe the outside air. This is going to be an issue as we go far into the future, maybe 100, sometimes about 200, 300, 400 years into the future. So this is something that's going to affect our grandkids or great-grandkids more than it's going to affect us. Now, if you're living in an environment where the atmosphere has high CO2, one of the things is going to exacerbate asthma. And so a lot more people have asthma. A lot more people will be prone to respiratory issues. People be on oxygen. It would be very common to see, kids with oxygen masks on at this time, or wearing some sort of scrubbing device. So we can deal with that, right? We're like, okay, we can do that. We'll wear masks when we're outside. We'll have, like, instead of space suits, we'll have earth suits, because in addition to being really hot, in addition to prices being really expensive and hard to find food, we can engineer our way out of this. We'll have to wear special suits, maybe cooling devices and stuff when we go outside. But inside, maybe we can have scrubbers like they have in submarines, so we could have balance out the atmosphere they're breathing. It doesn't make for say goodbye to those wonderful hikes outdoors. Or going, being outside and outdoors, everything's going to have to move indoors. That's kind of scary. That's a scary future. Things get worse though in the Permian-Triassic. If we use the Permian-Triassic as an analogy, because something happens in the oceans, and this is terrifying. So when you warm up the temperatures of the oceans and you basically start killing off everything in the oceans cover 75% of the Earth. They are a big part of the climate story. They're the big part of stabilizing the climate, and they're the big part of, like, if things go bad in the oceans, they can be really catastrophic for the rest of the planet. One of the things that starts happening at the Permian-Triassic boundary that's very, very terrifying is that the type of life living in the ocean changes. And that is because the oceans become anoxic. At higher and higher temperatures, they cannot absorb as much oxygen. This means that anything in the oceans that breathe oxygen die. These are referred to as dead zones today in today's oceans. They happen a lot off the coast of the Gulf Coast of Texas today. Big thing with fisheries because it kills off all the fish. Now, when the oceans become anoxic, and we're talking at the Permian-Triassic event, this event way back in history, it basically means that anything that breathes oxygen is not going to live in the ocean, which is pretty much all ocean life, except for bacteria. Now, the bacteria today, what's really terrifying the bacteria today is they need a food source. And they need, one of the things they start doing is they start grabbing other chemicals in the ocean. The one chemical that they will grab in the future, and they're grabbing, this is what's causing all the dead zones in Texas, off the coast of Texas, is nitrogen. Now, at the Permian-Triassic boundary, they were grabbing sulfur because there's a lot of sulfur from the burning of the coal entering the atmosphere. There's not that much sulfur because we scrub out the sulfur when we burn coal. We recapture that. But sulfur is a big issue. With sulfur, if you burn coal and you don't have it scrubbed out, it produces sulfuric acid. This is what kills a lot of people. This causes acid rain. It kills a lot of people in places where they don't regulate the burning of coal. So this caused great deaths in London during the 1950s and causes a lot of the issues in Beijing, in China. The unregulated burning of coal, really bad because of the sulfur. Sulfur and nitrogen are interesting because they both oxidize and they're both used by bacteria, different types of bacteria, but in the same way. These bacteria survive and thrive in anoxic environments. They do well without oxygen. In fact, oxygen is kind of poisonous to them. So to survive, they live deep in the seafloor, underground, where there's not much oxygen. Now, a lot of that oxygen is coming from the atmosphere. It decreases as you go deeper in depth. So these things live way deep down in the depths of the ocean. We talk about that methane coming out. Now we talk about this bacteria coming out of the ocean floor. This bacteria loves the anoxic environment. Now that the temperature is really high, it's a hot jacuzzi, these bacteria thrive in the hotter waters, and they come up. And they come up towards the surface. Now, at the Permian-Triassic boundary, what these bacteria were doing was they're grabbing that sulfur and basically reducing that sulfur. They would rip off the oxygen and use that energy to build their bodies. They need to get rid of that sulfur. So they would slam it with hydrogen, and they produce something called H2S. So it's basically H2S is a gas, and it starts to bubble out of the ocean. Now, most people who work in the oil and gas industry are very aware of H2S. So, and I'm sure you're in Dallas, but if you're down in Houston, if you're down in the Permian Basin of Texas, H2S is a big issue if you work in the oil fields. H2S builds up in oil fields just for the same reason. Deep down in these reservoirs of oil, there is bacteria that are feeding on the oil, and they're doing the same thing. There's no oxygen down there. It's a great environment for them to live. It's nice and warm. And they produce H2S. And H2S is a very toxic gas. If you breathe it in, you die at very, very low concentrations. So this is a big hazard for oil workers. You have to do training when you work in the oil and gas industry. And it builds up and can get released onto the surface. So when you drive across an oil field and you see the flares they're burning, it's not that they're burning oil or gas for whatever reason. They're burning H2S because you can combust it. It produces sulfuric acid if there's moisture in the atmosphere, and it strips off that hydrogen, so it's no longer as poisonous. Still not good to be around, but it's a way to get rid of it because it is very, very poisonous. But now we have the ocean filled with bacteria that are producing a lot of H2S. H2S, of course, is toxic, so anything that basically breathes this in will die. This is really scary because unlike a buildup of CO2 where you can scrub it out, the H2S, it's really nasty stuff. It's flammable. It's a fairly flammable gas, but it's a very heavy gas. It's going to sink down, especially coastal cities and areas, and that will just make the air completely toxic. Peter Ward wrote a really wonderful book about the Permian-Triassic boundary. He described that if this were to occur and get into the atmosphere, it would change the atmosphere so it would look green. The sky would be green, like a green haze. That event just starts to wipe out all of life. I mean, we're talking 97, usually the numbers around 83, 97, wipes out anything that's living in the oceans. Like most things die. So you're talking about pretty devastating consequences on life living at the time. So 83, 97%, it's debated quite a bit of how much life is completely wiped out because of this. So how do you just survive an environment like this? I mean, humans might be able to survive it. In fact, Peter Ward said, humans might be able to survive something like this because we'd become subterranean. We had filtered out the stuff. No one would go outside. We'd build cities and bubbles, things like that, to help mitigate with this. But it would be very devastating for life outside of that protective zone. The animals that survive this event are really interesting. So one of the things that survived and did quite well at the Permian-Triassic boundary were animals that had a couple of adaptations. One, burrowing, getting underground, having a respiratory system that could handle breathing high CO2. Thoraxodon, which I think you probably talked about in one of your videos, has these really big, huge ribs, very useful for breathing and being able to breathe air deep underground where it might be a little bit safer for them. So if these waves of toxic gases came over the surface, they would be protected deep down in the earth. So burrowing is a good adaptation. In the oceans and in the rivers, you see fish do quite well. Fish, anything that's mobile, anything that can move out of the way of these anoxic zones, can move upstream, could avoid these things. Now, if you're a fish and you move from the ocean into the river systems and get upstream in the rivers, you're dealing with an environment that's much more oxygenated. And those sulfur-reducing bacteria, that awful, nasty stuff, can't live in these really bubbly rivers. So if you think about fish, one of the reasons that they spawn, they come up the rivers, is because those rivers are sanctuary from a very toxic ocean. So it's kind of this wonderful holdover, a pre-adaptation or adaptation that resulted from this event. They still see in fish today. Their behavior is to get up in these rivers when they spawn, to lay their eggs in a safe place that's not going to be affected by anoxia or H2S gas or this nasty ocean that existed at the time. So it's a way to survive. And fish did really well. This basically caused them to be very diverse during this period, subsequently after this event. It's pretty bad. And you think, okay, how do we change? What changed it? How do we get back to temperatures that we have like today, where we have snow and things like this? And it took many millions of years. And in fact, most of the first period of the age of dinosaurs was this craziness of a climate that was just out of whack, that was just really, really different than today. So, that's where we could head. But there's a couple of things that say we may not head to that extreme. One is that there was no off switch. We have an off switch. I mean, it's very easy for us as humans to make that switch. And so we don't have to live in that type of environment. We can switch to renewables. We can switch to electric vehicles, use solar power, use wind, use hydroelectrical. We can basically start to mitigate the amount of CO2 that goes up into the atmosphere. So it never gets to that stage. Maybe we can survive, it getting a couple degrees warmer. But if you go into these extremes, then it can veer off into a really bad way.
So
Now,
people should realize that the Permian mass extinction, I think, was an initial rise of 4 or 5 degrees before that initial rise launched the next wave of that, which was the release of the methane, and then that launched the next wave, which was the rise of the anoxic bacteria that then produced the poison gas. And
yeah,
so,
it's like,
and so people are only thinking about, well, it's just a couple of degrees warmer. I can handle that. So it means that Phoenix will be 127 degrees. So what? That's as far as a lot of people are seeing this. But if you're studying paleoclimates, you're seeing a whole nother perspective that people need to know.
yeah, and it can cascade out of control over a long period of time. Now, the problem is we only live on the Earth. If we're lucky, we live 100 years. And many of these processes take about 1,000 years to play out. So you're talking about a world that is going to be inherited by your ancestors. So it's difficult. That's the hardest thing, I think, because politicians and politics is all about the now, the instantaneous. Whereas getting people to change that will affect their ancestors is difficult, or I mean, not their
Descendants. Yeah.
Yeah. So it's going to affect their descendants. It's going to be your great grandkids, and so that is much more difficult to make those changes because they seem remote. So they're not immediate. So even my students have a tough time understanding this because they're like, well, it's not going to affect me. And, even if I live to 80 years old and I'm happy in a nursing home, sure, it'll be a little bit warmer and there'll be forest fires all the time. And maybe there'll be sand dunes outside and maybe I won't be able to water my garden as much. But they don't realize that it's just a step in this direction. Now, the interesting thing is all of these events that I've mentioned have reversed themselves. The Permian-Triassic one took a long time to reverse, millions of years. But the Paleocene-Eocene thermal maximum reversed itself fairly rapidly. The Earth cooled down over a number of thousands of years, but it cooled down. So the question we can ask is what causes the climate to cool down? What can we do to to reverse this process? And there's something really interesting. So CO2 is used by plants. So one of the best ways to draw CO2 out of the atmosphere is to have more plants to support forests. Basically stop clear cutting, basically create green zones in cities, do massive replanting of trees because trees by themselves will draw down the CO2. In fact, in greenhouses, people who work in greenhouses worry about too little CO2 in a greenhouse because the plants in the greenhouse are using up all the CO2. So they have fans in greenhouses to bring in that CO2. So that's one way to stop it. The other way geologically is build mountains and cause erosion. Erosion strips out a lot of the CO2 out of the atmosphere through a chemical weathering process and redeposit it in the oceans. And that's another way that you can decrease CO2. But that's pretty impractical for humans to do, having giant, huge mountains like the Himalayas come up. But right now we have a lot of mountains. And so it's good. That's going to help mitigate some of that CO2 rise. So, I think we could panic. We could think, oh my gosh, we're going to head into the Permian-Triassic boundary in the future. Yeah, that's a contingency, but also we're humans and we can change that, as a collective, we can say, all right, we're not going to burn. We're going to cap the amount of coal that we're going to burn every year. We're going to search for other energy sources so that we can mitigate that and make sure that the planet stays healthy, that it doesn't veer into these horrible.
What do you think about there's, I don't know if you've heard about it, there's something they want to try in Harvard where they release calcium carbonate into the atmosphere, kind of like what you're saying, how a volcanic eruption will scatter ash and cool the planet. They call it like solar dimming or something. Yeah. And what do you think about this? I mean, the chemistry of it.
So basically, this is going back to James Hansen's, discovery that, if you throw a bunch of ash up into the sky, it'll cool things down. So that's like a short-term thing we could do. The problem, it's short-term. It's like a year to cool things down for like a year by doing that. And you got to realize the scale of the Earth and how much that would produce in terms of mining it, flying the planes to get it up there, launching the rockets. All of that's going to probably, the transportation cost of getting that up into the atmosphere is going to cause as much CO2 as it would be beneficial. Yeah. Into the atmosphere. So it's probably not feasible. It's fun to think about. In fact, actually a lot of climate modelers and people who play around with this will be able, in a computer program, be able like, oh, we could tweak the solar radiance. We could maybe put up a big, huge sun block or something like that up into space. How would that affect the climate? And it does. There's been some really fun computer simulations of playing around with those types of things, releasing basically things, aerosols or different types of things into the atmosphere to help block as a sun block. block the amount of solar radiation coming into the surface.
During the last solar eclipse, I was at I was at the right place to get a total eclipse, and I remember the temperature changing noticeably during that 2 minutes
Yeah.
that the moon completely obscures the sun. I mean, it got way cooler immediately.
So that's, if you could block the sun, it would definitely cool things down quite quickly. Um, but the practicality, that was such a small little pinpoint of a location that you had to go to observe that. And
Yeah.
so being able to do that across the entire surface of the Earth and do it in such a way that it doesn't cause the Earth to, I mean, it would be devastating if you did it wrong and we plunge into an ice age. So I think it's fun academically to think about, but I think the practicality of that they call geoengineering the Earth into a different climate is somewhat impractical with our
It's
current.
so much easier.
You'd have to get a lot of different countries to cooperate to do it too, to effectively cover the Earth.
It seems so much easier to just invest in green technology like China is. The way they put up all of these solar power stations. They have all of these windmills everywhere. They've got all these electric cars. They're doing everything they can to go green because they have the highest pollution level, right? But then we, as you mentioned, the pivotal thing was when George Bush did not win the election, but was given to him anyway by the Supreme Court, and we would have ended up with Al Gore, who of course was an environmentalist. So and he ends up losing out to a guy from the fossil fuel industry, and then the fossil fuel industry owns this country from then on. And it's like we were talking about with the people that are promoting tobacco. If they're in the pocket of tobacco, then cancer isn't an issue. The cancer is caused by something else. It's just coincidence that it happens to happen to people who smoke, right? Because that seems to be the way that they're thinking. So how far can I push the boundary before I have to accept the reality? Look at Trump and the recent the recent science report. He's denying his own science, saying, "Oh, I don't believe it."
Well, and the other thing is to look at one of the interesting things that's happening, I think, today. So many of my students work in the petroleum industry. I've had students who work in coal mines, and that's where they earn their money. I mean, if you think about it, when to make a living in this country, you have to get what people are demanding. You have to provide a product. And I think one of the things that we're seeing across the world is that the global economies are switching from one that's based on coal and petroleum to one that's based on technology, on solar and electric vehicles, electric engines, switching from the combustion engine. And the way I see this is a natural progression. And governments and politicians, especially in the United States, I think are extremely stubborn in trying to revert and trying to slow that down as fast as possible, that change. Whereas other countries like China and Europe are trying to speed it up. I mean, the protests that are happening in Paris over increasing gasoline prices is a response to people being like hesitant and not wanting to make that sacrifice. So it's a slow process. It's something that's going to be played out over many administrations. And I think that one of the things that's interesting is that you can step back from it from a geological point of view and take a deep breath and say, these things have happened in the past and it could go really badly in 1,000 years. But we are humans. We're smart individuals. We've been placed on this planet to help, regulate it. And one of the things that we can do as a collective, as Earthlings, is to start making those changes. And it can be very subtle, can be very small. Switching, so many of my neighbors, even in a town run by oil and gas, are switching to solar panels on their car or on their houses. And they're putting up these solar panels on their houses because it's economically viable. It makes sense. They don't have to pay the coal power plant as much money. They don't have to worry about electrical outages. It's very practical reasons that are making this change. So one of the things I think governments could do better at and politicians could do better is nudging that just very slowly. And it's maybe slapping a small tax on gasoline, which is very controversial. Maybe it's one of the big things that came out is prohibiting drilling on public lands. 25% of the CO2 produced by the United States comes from public lands. It comes from land that's owned by the government that they subsidize and promote people to drill on. So just restrict that. Just pull back a little bit on it, every few years until you eventually phase it out. So there's ways we can phase these things out. And politicians, I think, in many ways, they talk the big talk to the constituents, and then they go back and they are always listening to probably the wrong people to listen to. Instead of listening to the citizens, they're listening to these lobbyists. And many of the lobbyists themselves are driven by changing people's opinion, not necessarily trying to look at the facts and trying to think of solutions. So, yeah.
Oftentimes politicians kick the can down the road, or they listen to people who have lobby interests, like Trump is going to sign a law that they can use air guns to test for, you probably know more about this process than me, to test for oil in the Atlantic Ocean, and Obama refused to sign that. So where is the point of no return? Is it 2 degrees or 5? Where do we reach a point where we can't, where it is not possible to reverse or mitigate global warming?
So I think the point of no return is going to be at the point in which you start noticing things. So for the point of no return for somebody in California that's house just burned down, it was, a decade ago.
Mm-hmm.
For someone that's living, at a ski resort and there's no snow at the ski resort and they have to close the business down, it's when they close that business down. So it's just going to depend on where you are and how you're impacted by these events. If you are in New York and the subway systems get completely flooded out because of rising sea level and you can't take the subway anymore, they'll be that day. So each of these events are going to be those days. And so
isn't the 2-degree rise in the near future if we don't do more?
Yeah, so the Paris Agreement has been trying to set these limitations. So we're not going to let it go up to 2 degrees is sort of the idea. Now, that's one way that's one metric that we can use. Probably a better metric would be how much CO2 is in the atmosphere, because we can look at that measure of that station in Hawaii that Keeling started up so long ago. We can say, okay, is 500 parts per million permeable? Should we stop there? Is 1,000 parts per million, or is it 5,000? That might be a good metric to use. Temperature is a little bit crazy because you have to average like a lot of data.
Mm-hmm.
And when you're talking 1 to 2 degrees, it's going to be kind of scary to get that data coming in. Carbon dioxide might be a better one to look at. And one of the scary things about carbon dioxide is that it's starting to turn exponential. This is because there's much more vehicles on the road today than there ever has been. There's many more people living today. There are many more people using energy, releasing
beef,
while also deforesting on a major industrial level.
Deforestation is a huge, huge factor today. All of those things are contributing to the rise of CO2 in the atmosphere. And it's exponential. It's just increasing every year. The rate is increasing every year. And so what we really have to worry about is slowing that rate down so that rate starts to change. Many countries you're starting to see better fuel economy. You're seeing better use of the resources that we have. We're starting to see alternative energies come online. So I'm hoping, and everybody's hoping, that it will start to plateau and that that curve will start to slow down. It won't be such an exponential curve. It doesn't look like it is. I mean, part of the problem is that the way to make money and the way to move the economy is to produce these products, and coal and oil and petroleum are highly desirable. What we're seeing with the drop in price recently of oil and petroleum, to 50, 55, dollars a barrel, it's kind of interesting because I think a lot of this is driven by the people using alternative energy, the rise of electric vehicles, where people are not filling up the gas stations. And so this is an economic response to drop down those prices. It's interesting because one of the big fears is running out of oil for the country. The United States had the peak production of oil in the 1970s. It's never produced as much oil as it did in the 1970s. That means the amount of oil that's being produced in the United States is decreasing. It's been decreasing since the 70s. There's a little funny blip up there because of the fracking technologies that came online a few years back. But for the most part, the production amount of petroleum in the United States is dropping. So eventually we're going to run out of that petroleum that we can use in our vehicles. And that's going to, as we move to other alternative energy sources, that's going to dictate really what's going to be happening. So, I think that we can really drop off our production of those things in the future because of new technologies coming on. They're going to be more convenient. Having to drive to the gas station to fill up the gas, and then getting a mile for every gallon, 10 miles for every gallon or whatever, old junker car. It's just not going to cut it. It's not practical in the future. It'll be fun for antique enthusiasts, just like steam locomotion is fun for antique enthusiasts today. But we're moving into the new future, and I think
you're saying that CO2 production will drop from its current levels.
Yeah, we're just running out of oil. Yeah, I mean the big scary thing is coal because we have a lot of coal. Coal is my biggest worry is coal, and I know Trump is a huge supporter of the coal industry, but coal is really there's no such thing as clean coal. There's in many ways coal is a very old technology, and we have lots and lots of coal. The more you do mountaintop removal, the more you get down to those layers. That Carboniferous period, there was a lot of forests that were drawing down CO2 and producing a lot of oxygen that we enjoy today. So coal is a big worry. I mean, coal is what caused the Permian-Triassic boundary extinction. So and I think that's the biggest worry. So I think solar is going to be the way forward. I think nuclear energy is very viable and should be considered as well. It doesn't produce CO2. It's carbon neutral. And I know many people are on the fence with the nuclear, but it is a very viable way of producing energy. Many countries are fully nuclear in terms of their energy generation.
Yeah, well, we can talk about Fukushima on another show. But I want to thank you for being on. We asked you to do 20 minutes to an hour. And it's been an hour and a half. And so, Lalandra, did you have any questions?
Yes. You're at the University of Utah, right?
Utah State University.
I got it backwards. Okay.
And I'm at the Basin campus. So like UT Arlington or whatever, we have a campus in Vernal, which is where I'm at, which is we call it the Uinta Basin campus. It's in the tri-state area of Colorado, Wyoming, and Utah.
How long have you been studying paleoclimatology?
Oh, let's see. I really started getting interested in paleoclimatology. Let's see. I would say about 20 years now.
Mm-hmm.
I started working on trying to find the Permian-Triassic or the Paleocene-Eocene boundary.
Mm-hmm.
I did some field work on that in 2002, I think. And I've been a paleontologist longer than that, but
is the Paleo-Eocene boundary in your area geographically?
Yeah, so both of them are near me. So I actually just submitted a paper. I'm hoping we'll finally get revisions of hopefully get published on the Permian-Triassic boundary in the Uinta Mountains. We have a really wonderful section through that layer of rocks. And then the Paleocene-Eocene boundary is found across the border in Colorado, where I've been studying it. And I think there's a really good exposure of it in southwestern Wyoming that I've been trying to find and looking for it out there.
Is it one of the pictures in your background? The boundary? Is it exposed in one of the pictures?
Yeah, I got
in your background.
Boundaries. Yeah, so like the Permian-Triassic one is one of my background pictures. Yeah, so some of these are different places that I've done field work. I don't have any. I need to paint a painting of the Permian-Triassic boundary layer.
Yeah, I also want to throw out a thing for anybody listening. Benjamin Berger was a consultant in my systematic classification of life videos for I think at least 3 videos. I had to turn to Professor. Is it fair to call you Professor Berger? Or
Yeah, that's fine.
Okay. So thank you very much for that, because I mean I know a lot of this stuff and I can research a lot of this stuff, but there were some places where I need a professional to help.
Well, yeah, especially the placental radiation of mammals gets really complicated, and there's not that many fossils. We need to find more fossils of some of those creatures. I would love to get some more skeletons of some of the early Paleocene stuff.
The pictures of them, they're always maybe either furry or a little smooth looking with a little hair. Yeah. Or some of them spiky or...
Probably. We just don't know.
Like a pangolin with scales or dermal scales or stuff like that.
That would be...
She has an interest in the evolution of pangolins, so if you can refer us to somebody that can help out with that, we'd like to talk to them too.
Oh yeah, so pangolins are really fascinating. I have a video on pangolins if you look it up on YouTube. They have a really fun fossil record. The world's expert is probably a good guy to talk to would be Ken Rose.
I did contact him by email, and he emailed me back for a project I'm doing. I'm in a science writing program at Johns Hopkins, so.
Oh, excellent! Well, you're at Hopkins, yeah, definitely, yeah.
He's at Hopkins too, so.
He's definitely the expert. Yeah.
Well, it's kind of fun to picture maybe what they look like, and maybe they have more diversity than how they're depicted in paleo art.
Yeah, definitely. And the sad thing is that most of the Eocene guys and the Paleocene ones we have for North America are just jaws. And stuff. There's the best one that we have is Metachiromes from the Eocene of Wyoming. And they're the ones with the little canines in the front. Some spectacular skeletons have been found. I worked with a colleague up there who had found some really amazing skeletons of Metachiromes, one of these really primitive pangolin-like creatures. And there's no evidence they had scales, so we have no idea what its body is.
Can you look at some of the current mammals that have survived without being radically changed in their appearance to kind of guess at what they looked like before?
Yeah,
like
definitely.
Look at a pangolin now.
Look at a pangolin now. And keratin actually is interesting. So keratin that the pangolins make their little shells out of, the little scales out of, can fossilize occasionally. So you can get some keratin sometimes in some of these really remarkably well-preserved specimens. The ones that they discover in Messel don't appear to have, in Messel, Germany, in the Eocene, they have some really wonderful shale, they're in shales that have been compressed. And they don't have any indication that they had keratin scales. It isn't until you get to the ones in Asia and in Africa that you get the living today that you have definite proof that they have these keratin scales. But you can try to get it back. You can look at the common ancestor of those and realize that this Eocene one didn't have scales, and so it might have occurred somewhere between the two in terms of evolutionary tree. So
when they look at feather evolution, they have intermediates, and was it all of a sudden fur or from scales, or were there like intermediate steps?
There probably was. Yeah. It'd be fun to research that and see what the individual steps.
Well, we are on a different topic now. So, we've been a really long time on this episode, and I want to thank you for it. I found it very interesting, and I do think it is important information, especially when I live in Texas. And as you know, the people here just wantonly deny that they have any responsibility. It's not just that we're causing climate change. It's like they wanted to deny any responsibility for anything. I don't have to change what I'm doing to benefit future generations or to take care of the environment or whatever. It doesn't matter. I think Trump even said this. It's not going to matter what happens, 30, 40 years down the road because I won't be here.
Yeah, and I think that there are people that are that way. They don't really care about these things. The things that they care about are when it impacts them.
I was raised in Houston for 30 years, and they would have one tropical storm, one 500-year flood, and they would just rebuild in those same floodplains. It was flood, rebuild, and Harvey got their attention because now because of climate change, warm air holds more moisture, and you're going to get bigger hurricanes and more flooding in low-lying areas like Houston, and now they're talking about building a seawall, a sea barrier. They have a seawall in Galveston, but a more complete one. And people say maybe to protect their oil assets there, because I think they drop a lot of oil off to get refined or something like that there. And and when it starts costing, everybody always looks at I'm going to die scenarios. But when it starts costing people a lot of money and the right people a lot of money, maybe that'll get people to change. Because the Harvey was, I forget how many billions of dollars of damage. And now they're starting to try to maybe think about repurposing defunct golf courses to build water retention and repurposing landfills for water retention. And so they're starting to look, but they kind of still are building in floodplains, but they're doing baby steps. And they said maybe you have to be about 2 feet above the 500-year flood level. And so maybe that's some hope. I mean, things are already getting worse without that 2-degree change.
Yeah.
In Florida, Houston.
Things are getting bad. I was looking at the pictures of the people in Venice going to their favorite restaurant that are open, even though there's like a foot of water inside the restaurant.
Yes. And I think hurricanes maybe will head a little further north too because of the warming temperatures in the ocean.
Yeah, so sea level rise is going to be huge issue for coastal cities. So it's going to affect decisions like, do I buy this house that's next to the ocean or do I not? And so it's going to affect housing prices. It's going to affect the way you sort of think about things. So economically, it's going to have an impact. If your favorite restaurant or your house gets flooded, you're going to be much more, an advocate for changing and making change. So it's going to be won the hard way. It's going to be won by people's pocketbooks. It's not going to be won by convincing them on a show like this or on a website or something like that, a YouTube channel. It's going to be when your house burns down because of a forest fire, or it's going to affect you if you have a family member who dies from heat exposure. So those things are going to be the things that are going to drive people. And it's a slow process. It's not necessarily something, and there are going to be advocates. I mean, it's like trying to convince someone who smokes to quit smoking. Well, this one cigarette is not going to kill me.
Right.
So it'll take 7 years off my life. It's the last 7.
This one is not going to kill me, but it's the accumulation, and that's hard. That's hard for human psychology to deal with. And so it isn't until you have, be diagnosed with lung cancer that you go, oh, maybe I should stop smoking.
Yeah, my dad died of emphysema caused by smoking. So
it's hard. It's a hard decision to make. Yeah.
Well, some of the laws helped out too, like non-smoking areas. And at one time, if you get in an old plane, they'll have a blank in the place where the ashtray used to be. So you're sitting there smoking on an airplane. That's crazy.
I know, it's crazy, and it's crazy to think about. Growing up, and everybody smoked back then, and now people like look at smoking and like it's banned, even in Disney movies and things like that. So these things change. They change, and they change over a gradual period of time as people realize these things. There are still people who smoke, but the number of people smoking is decreasing, and so we're going to see the same thing, I think, with climate change. I'm hopeful for it.
What about beef eating?
Yeah, beef eating is interesting. I haven't looked much at the research of that. And it is something a lot of people bring up in terms of one of the reasons that beef is so bad is because of clear cutting and deforestation, particularly in South America, where there's a lot of beef being produced in South America. Up here in Utah, where we're in desert and there's still a lot of beef being produced and cows, they're in areas where there's tight regulation on overgrazing, which would be an issue. But for the most part, they're fulfilling the niche that the buffalo had, that other animals had in the past. So I'm not too worried about, it's nice to be a vegetarian. I'm vegetarian, but I don't think that the beef industry is some place to really go after in changing things, because I think it just depends on where those cows are being raised.
Are they producing a lot of methane though?
They do. In fact, actually, it's interesting, but they're not producing as much methane as, say, coal bed methane, which is a process where they convert coal into natural gas, which is really common in like the San Juan Basin, New Mexico. And if you look at some of the methane satellite data that's come in, that's a hot zone. Yeah, you have hot zones above dairies, which is a big issue. Dairies produce a fair amount of methane because the amount of methane being produced by the cattle, especially if they're all in one area. And there you're talking more dairy products. So, if you're talking avoiding dairy products, that might be if you want to make an impact. But to me, it's pretty minor compared to other bigger things like deforestation being much more of an issue.
I'm excited for beef alternatives like clean meat. Yeah.
Yeah, it'd be interesting. Yeah.
We're both kind of curious about what can they do with Franken beef and other artificial meats. Well,
it's funny because you have the gluten craze. Gluten is a replacement for a lot of beef for a lot of people. Now it's like forbidden to eat gluten, so it's difficult for a vegetarian who's trying to find meat alternatives. Yeah.
So I'm gonna go ahead and close it out. Honey, did you have any other questions that
No.
are pertinent to the subject?
Thank you for being so informative, and thank you for your time.
It was a lot of fun, and I'm glad I was able to answer your questions. Hopefully, kind of talk some stuff. If you have any information, there's a lot of really good websites out there for climate change or for all this stuff. So
that reminds me, you have a YouTube channel.
Yep, I have a YouTube channel.
Put the link for your website below. And the link for Dr. Berger's website does have his YouTube link on there as well. He does a series on, well, you explain what the series is.
Oh, well, so I'll give you a quick background. So I teach here at the Utah State University, and I teach a lot of online and broadcast courses. So in 2012, 2013, I was using a service to do my courses, and I started playing around with YouTube because it had the best buffering rate of the video providing services out there. Really great buffering rate. And so I started just making funny, silly videos that I put up on fossil mammals, which is my own interest, just to play around with it. And then it worked really well, and I just made them public. And then since then, I've been making videos, course-related videos, but I've also been doing ones on Utah geology and paleontology, so with a focus on geology and paleontology. And I think I'm up to like maybe 250 videos online. They're available on YouTube. And they are kind of related to courses that I teach here, but a lot of them are just expanding on stuff. And so they're really good toolkit. A number of universities use them for just teaching, especially in smaller universities where they may not have a geologist or paleontologist to teach some of those classes on staff. So just provide extra material on it. So
I've certainly used that resource in my series. I've watched a lot of your videos on that.
I'm gonna watch the pangolin video.
Yeah, check out the penguin one. Yeah, that's a really fun one. I can send you a link to it. And there's a lot of so now I do any topics, and now that I have enough people who are watching, I've been getting a lot of suggestions of where to take it. I also do a series called Rocks of Utah, where I go to I have one on the Permian-Triassic boundary here in Utah, that I go out and just film my research and film me just doing a field trip to a place in Utah and look at the rocks. So
I have a question. This is a special question. I've been trying to get an interview with somebody that personally does radiometric dating. I want it because I'm always arguing with young Earth creationists who insist that there is no geologic column. They're really into the science denial thing. So I mean, every layer that you've been talking about today, some evangelist is saying none of those layers exist. So everything you experience is an imagination, I guess. They also denied that there are any radiometric dating methods that actually work. And so I want to talk to somebody who personally does radiometric dating to dumb it down themselves, to explain to the audience how it works. I mean, I know I can explain it, but I'm not the guy who does it, and I want the guy who does it to explain it.
What you could do if you want to do it is grab some rocks to take into date, and you might. So one of the things I've discovered working with labs that do dating, probably the dating that they do now is mostly zircon dating. So zircon dating, you basically grab some volcanic ash or something like that. They basically grind it up and then separate out the little teeny tiny zircon crystals. These zircon crystals have a little bit of the uranium and lead, and then you basically zap it with a what's called an ICP-MS, which is a plasma mass spectrometer. Many labs actually have a plasma mass spectrometer. What they do now is what they call laser ablation, which means they shoot a laser at it, and it basically produces a puff, and then they measure the chemistry of that. They take that little puff of gas and they throw it through a plasma, and they basically throw it down the plasma. Depending on the mass of each of the atoms, it hits a little counter. And then they look at the ratio between the lead and uranium. One of the things, if you're doing uranium lead dating, that's very common today is there's something called the congruent curve that they apply, so some mathematics is required. But one of the fun things you could do is contact one of those labs that do that, take in a rock sample, and then talk about every single step. Because I think a lot of I have steps on how to measure a mass spectrometer on my channel, and a number of people approached me and said, "Oh, I've never seen a mass spectrometer or how it works." We're familiar with clocks and how they work, but we don't necessarily wander into.
Have you ever done your own radiometric dating?
I haven't. We have an ICP-MS here that's not running, and there is we have a mass spectrometer that can do radiometric dating, but it's set up right now to do just bulk sediment geochemistry. But there are certain labs. I think the University of Arizona has one. The USGS has one. Actually, the public can send rock samples to the USGS and they do it. It's kind of expensive. In fact, I sent some of my stuff up to a person that did when I was doing my dissertation to get some zircon dates, and it cost me $1,000 to do. So they can be kind of expensive to run on the machine, because they take the rock, they got to find the zircons, they study the zircons underneath a microscope to make sure that they are fresh, that they're not like an old one that's got mixed in, what they call a detrital zircon. Sometimes they'll just do the actual technique of measuring that ratio is actually not that expensive, because they just zap it with a laser. They can do a whole bunch very quickly. But it's the physical process of finding that little teeny crystal, mounting it, studying it under the microscope, and isolating it, making sure they're hitting the right spot, because they're not hitting the substance next to the crystal, which would give you a wrong result. So yeah, it's a little technical, but it'd be fun to talk about it.
If you can get me in touch with anybody that personally does that type of testing,
yeah,
at any of these labs. I mean, I don't want to go in. I obviously don't want to spend $1,000. I don't want to hunt down a lab and then walk into it and talk to somebody there. I want to get somebody on a podcast like you're doing right now.
Oh, okay. Yeah, yeah. I could send you some emails of some people that do mass spectrometry work, whether it's dating
Please.
or.
Yes, thank you. Anybody that would be willing to come on for just long enough to explain the process. It doesn't have to be an hour and a half. Well, an hour. We're climbing up the time on this one. I'm going to have to cut this show the show off here, and I want to thank you again,
Oh, no
Professor,
problem.
for being on.
Yeah.
And I will invite you to do another podcast when we can find something again that's relevant to your field.
Well, certainly. Yeah, yeah. If you have any more questions about paleontology, geology, any of those topics, I'm happy to answer them. So, yeah.
All right, and links below. Thank you very much.